Hello everyone, and welcome to today's Energy Storage News webinar with PowerUp, where we'll be talking about the economic benefits of cloud-based analytics for battery storage assets. Now, lithium-ion batteries had already transformed all of our lives, long before they became the technology of choice for stationary battery storage. So much so that in 2019, three of its inventors, Stanley Whittingham, John Goodenough, and Akira Yoshino, were awarded the Nobel Prize for their discoveries 3 to 4 decades previously, and the contribution lithium batteries have made to humanity ever since. Who knows today if, in years to come, some of the pioneers that then brought lithium-ion batteries to the grid, storing renewable energy, helping stabilize and balance our supplies of power, and bringing power to people in remote areas that otherwise could not have had it, might one day be awarded their own Nobel Prize. Well, much like the collaborative efforts of Whittingham, Goodenough, and Yoshino, the energy storage industry is a sort of team, working across geographies and different areas of technical expertise. Much less heavy, much longer life than lead acid, much cleaner than the fossil fuel technologies we are working away from dependency on. One of the lithium batteries' key characteristics is also the ability to digitally monitor and manage each device and how it operates. That ability is absolutely crucial to the business case for using batteries. They are not a dumb technology that simply plugs in and goes, or are on and off like a light switch. Using batteries smartly will separate the leaders from the followers in the energy storage industry and will often dictate success or possibly even failure for large-scale battery storage projects. Today's speakers are all experts in that regard, getting batteries on the grid to operate safely with high availability for the longest lifetimes possible. Joining us from PowerUp are Philippe de la Fortelle, who's Chief Revenue Officer, and Dr. Arnaud Delay, who is Chief Science and Innovation Officer, to talk us through some interesting case studies which exemplify these concepts perfectly. We're also very happy to be joined by Aurélie Moine, who is Head of Energy Management Systems at renewable energy power producer Akuo, who can give us a customer's perspective on PowerUp's analytics solutions from the field. Now, as always, interaction with you, the audience, is very important to us. So please put your questions for the speakers in the tab on the right-hand side of your screen. Given the limitations of time that we have today, I can't promise that we'll answer all of your questions, but we will do our very best. And in the cases where we can't get to them in time, or if perhaps they're a bit too detailed to go into within this public forum, the experts from PowerUp will be more than happy to continue that conversation and answer your questions offline afterwards. Oh, and finally, today's session is being recorded, so everyone who registered will be able to access the on-demand version to watch again, and I believe we will be sending out presentation slides afterwards to your email addresses. So, with all of that housekeeping out of the way and that introduction from myself, I'd like to hand you over to our first speakers from PowerUp, Arnaud and Philippe. Over to you.
Hello, everyone, and thank you, Andy, for this very kind introduction, and thanks to Energy-Storage.news to give us the opportunity to present you PowerUp. So in a few figures, PowerUp has a strong technical heritage. PowerUp is a spin-off of CLE10. The CLE10 is a French research institute working on lithium-ion batteries now for more than 15 years. PowerUp was founded in 2017, and we are now more than 35 employees with data scientists, battery experts. We have a portfolio of more than 10 patents on non-intrusive battery analytics solutions. And so we developed embedded software and cloud analytics solutions for various applications, among which we have BESS, of course, battery energy storage systems, but also electric vehicle fleets and backup system. So let's start this webinar with this first fact. I think we are all convinced that batteries are going to play a key role in the energy transition, but at the same time, we see that battery operators face to certain difficulties in managing their batteries. One first well-known difficulty is the battery fire risk. That means the risk of thermal runaway of lithium-ion batteries. We can say that this phenomenon is a destructive chemical reaction, very hard to stop when started. And so it's very important to develop some solution not only to stop the thermal runaway, but also to prevent such an event.
Hi all, glad to be here today. So thanks Arnaud, and indeed another hurdle affects performance, as it is sometimes extremely difficult to comply with the energy power levels dictated by the service level agreement under which the asset is operated, either because the battery faces limited limitations or due to the bad measurement accuracy. So that's hurdle number 2. Finally, moving on the right-hand side, battery assets are meant to last for a long time, sometimes more than 15 or 20 years. Predicting their useful lifetime, that is, until reaching a certain state of health threshold, can be hard because of the non-linear behavior of battery capacity, depending on intrinsic performance and usage.
So after this first fact, in fact, we are more than happy to say that now battery assets can benefit from new innovations capable of ensuring a higher level of safety, performance, and endurance. If we look at the safety, we can have an extra protection layer focusing on early signs of future thermal runaway events. If we look at the performance, we can maximize the available battery capacity through highly accurate state of health, state of charge indicators, among others. And finally, regarding the endurance, we can predict what we call the remaining useful lifetime according to the real usage conditions. But the best thing before going into detail of these solutions is to let the floor to Aurélie Moine from Akuo to tell us how a battery owner and operator see the benefits of battery analytics for their own asset. So please, Aurélie, the floor is yours.
Yeah, thank you, Arnaud. Hi, everyone. So my name is Aurélie Moine. I work at Akuo as head of the energy management systems. First, I will give a brief presentation of Akuo. So we are an independent global renewable energy power producer and developer. The company was created in 2007, and we are an integrated player because we are present on the whole value chain, from project development to operations and maintenance. We are based in Paris, but we are present in more than 20 locations around the world, and we are more than 450 employees. We work on several technologies, so wind, solar, hydro, and of course storage. And our capacity in operation and under construction includes 1.5 gigawatts of electric power and over 130 megawatt hour of storage. We also have a 20 gigawatts pipeline. So next, this is a map here showing our locations worldwide. As you can see, we are present in various geographies, from North America to Australia and Pacific, but also Europe, Africa, South America, Indian Ocean. But now let's focus more on storage because this is the subject of the day. So Akuo's battery energy storage system install capacity continues surging. We currently operate and construct over 130 megawatts hour of storage assets, but we have a 3 gigawatts hour project pipeline. And we use both NMC and LFP technologies. As you may know, lithium-ion batteries are a newer technology. This technology has been massively used since only about a decade, and the technology continues evolving very quickly. there are various chemistries, for example, NMC, LFP, but also sodium and solid states. And for a given chemistry, there are always different versions of it. As a result, there are only few actors who genuinely know how to operate them in an accurate way and genuinely understand this technology. Yet, it is very important to accurately operate this technology and really understand them to be able to operate the storage assets in a safe way and also enhance performance. So in this context, at Akuo, we decided to carry predictive maintenance projects means to be able to reach this goal of enhancing our safety and performance of our storage assets. This is why last year we contacted PowerUp in order to do a proof of concept on one project. And we were happy with their professionalism, so we decided to carry a live test. So the live test is running over 1 year, and it's running on 2 sites. The first site here is Madinina, which is located in Martinique in the French West Indies. And it is a 19 megawatt hour storage plant that is dedicated to frequency regulation. One of the specificities of this plant is that we have a 99.9 ratio availability guarantee, which is quite high. And so then the live test is also running on the Kuita project here in New Caledonia. This is a 3 megawatt hour storage plant coupled with a 6 megawatt peak of solar plants. The goal of the batteries here is to do renewable firming and load shifting. And this plant is, the strategy of the plant is run by the EMS that we've done in Akuo. So in the context of this test, PowerUp uses historical data and live data of both plants in order to determine state of safety indicators. They update every day these indicators, and we, Akuo, are able to monitor them through their platform called Battery Insight. The goal for us of this live test is to evaluate PowerUp's ability to detect potential battery safety failures on our plants well before they would occur, in order, of course, to be able to keep them from happening, and therefore enhance the safety and the performance of our plants. The test is still ongoing, but we are satisfied so far. Now we'll leave the floor to PowerUp so that they can give more details about the analysis that they're conducting.
So thank you, Aurélie. And I have to say that we are very proud to work with Akuo on this project. Just before describing different use cases with Philippe, we present here a brief view of the cloud platform we developed at PowerUp, and we call effectively it Battery Insight. The goal is to help battery asset owners, integrators, and operators to maximize their return on investment. So how does it work? First, we are going to collect the raw data from the SCADA, means the data acquisition system, all the different measurements we have from the BMS, the battery management system, and more especially, we collect the current, the voltage, and the temperature. Then we're going to clean and to process this data to calculate the different KPIs, effectively the state of safety, state of health, state of charge, remaining useful lifetime, and so on. And finally, all these KPI can be accessed via our dashboard, effectively, or directly via APIs to be integrated into our customer own dashboard. So now let's focus on different use cases.
Yeah, that's great, Arno, thanks. And I think that's the right moment where we should come back to the core subject of this webinar. How is this Battery Insight platform used to provide the economic benefits we described at the beginning of the presentation? So let's take a look at our first use case on safety. Of course, any safety event leading to a fire or sometimes just to an emergency asset shutdown to prevent a fire has a significant and adverse impact on the asset business case. Let's take this example of a 35 megawatt hour stationary asset that faced a 2 months shutdown due to a faulty rack that nearly took fire. PowerUp's retrospective analysis made clear that our cloud-based battery analytics system could have identified early signs of the degradation 9 months in advance, thus making it possible to swap the faulty module in the rack and to prevent the associated performance decline that we measured to be about 10% of lost energy. So we've set the scene on this first use case. Now let's look at the additional costs that such an event can create. Not only would revenues be lost by the container shutdown during those 2 months to test the various racks and modules with a maintenance crew on site, but also the performance limitations created by the problem would weigh on the available energy, and thus also on revenues not being able to be created from that issue. Here we used average euros per megawatt hour in a country where the issue happened. And so we computed these numbers, and the 90k euro result for lost revenues and additional costs does not even take into account potential penalties. If the 10% performance loss, for instance, would have prevented from complying with the contracted service level, or potential increased loss of revenues if, for instance, the energy market price would have skyrocketed during that period versus average prices. So all in all, this is a large savings potential, really making the case for battery analytics. But let's look at a second use case, Arno.
Yeah, we just saw that safety and performance were linked in the previous use case. Let's now focus on the second use case that illustrates the impact of cell imbalance on the performance only, before leading to any safety issue. So in this example, we analyzed data from a 32 megawatt hours battery asset used for frequency regulation. Now, what we see on this graph is the available capacity of all the racks in blue compared to the nominal capacity expected in orange. So you can see that due to cell imbalance issue, the entire asset was only able to provide 84% of its nominal capacity in average. That means a significant potential annual revenue is missing at the end of the year. The explanation is that cell imbalance is effectively a source of battery degradation that can lead to thermal runaway in the long term, but it can also introduce immediate performance issues. And finally, it's very important to notice here that once we detect such cell imbalance, such unavailable capacity due to the cell imbalance, sometimes it can be resolved either by cell balancing procedure or by replacing the limited module, depending on the root cause of cell imbalance, in fact. I move to the next use case. And here, another source of great economic benefits is the replacement of field operation with remote monitoring. What we see on this other graph is our capability to perform opportunistic state of health diagnosis during operation. It corresponds to each cycles in green. And if we focus on this state of health diagnosis, typically battery assets are tested annually or several times a year to assess the state of health, what we call the remaining capacity, through the capacity test or checkup. And it means with a full charge following by a full discharge. And all this checkup lead to a loss of service, of course, and to field operation, which can at the end amount to several tens of thousands of euros or hundreds of thousands of euros, depending on the size of the asset. And we can underline here that these activities may be required at least once a year during the warranty period for contractual reasons, of course, but hence they can be supplemented during this period, and even possibility we can replace these checkups by analytics, and so save a lot of money at the end of the year.
Thanks again, Arno. Let's move now to maybe more immediate performance issues that have to do with state of charge. This fourth use case describes another operational hurdle that has to do with the specificity of LFP battery chemistry. Indeed, LFP makes it very difficult for battery management systems, or BMSs, to accurately evaluate the state of charge of a battery asset, which again affects asset performance and returns. Battery manufacturers recommend recalibrating battery management systems very frequently in this case to avoid measurement inaccuracies that we call deviations or drifts. PowerUp's cloud-based platform is actually able to measure the state of charge accurately from past days data and compare it to the BMS state of charge, thus evaluating the real measurement deviation on a continuous manner. And this comparison enables a more efficient control over the BMS. Recalibration can be initiated only when needed, as opposed to doing it blindly every now and then. Since recalibration procedures induce loss of service, this capability will again provide economic benefits that can become quite significant across the asset life cycle. Finally, another wish from our customers and prospects is to extend the useful lifetime of their assets as much as possible. And this in order to have the greatest possible return on their initial investment that can be quite huge. In this use case 5, we simulate the capability to optimize and prolong the asset lifetime via PowerUp's continuous computation of what we call the remaining useful lifetime per container, per rack, and even per module. Here again, it will be possible to augment the lifetime via a complete control over usage parameters like cycling, temperature, and also via a preventive maintenance activity to replace limiting modules having shortest remaining lifetimes. Thanks to this continuous monitoring and optimization, a simple 10-15% life extension can lead to very large additional revenues in the millions of euros. Back to you, Arno, to conclude on this.
Yeah, to conclude, and just to before having the opportunity to answer the questions, we can conclude that Battery Insight solution is an advanced monitoring solution for battery asset management. It's, as you have seen, simple to use, completely non-intrusive, and it offers a continuous capacity for improving safety, performance, and endurance with economic advantages, allowing a very fast return on investment, even from the first year. So thank you. And now I give the floor to Andy for the Q&A session. Thank you.
Fantastic. Thank you so much, everyone. Some great presentations there. So much so. Oh, by the way, yes, you can meet the team at PowerUp at those events on the screen there at the moment with Philippe's email address very helpfully on there. And of course, you can visit their website, PowerUp-technology.com. Yeah, so again, thanks very much for those presentations. I can see, you know, we've got lots of people attending today, and quite a few of them have asked some really good questions, ones that certainly are way beyond my capability to reply to. So I'm glad we've got expert speakers with us. But before we do that, I will exercise my editorial privilege a little bit, and perhaps if I can ask our speakers some questions myself, we'll have a short panel discussion and then get on to those excellent audience questions. So yeah, I mean, I think if I could just say a very general point, I guess, or journalist's very general point before we go, you know, Arnaud, you mentioned that, you know, depending on the size of the asset, calibration tests can cost a lot of money. And I think that's really something everyone needs to bear in mind here, isn't it? Because we're seeing not only that projects are getting larger and larger, but we're seeing more and more projects. So any of these problems that go undetected, they will really be amplified, and you know, the urgency of the need to solve them, I think, really becomes amplified as well. So again, I'm glad we're able to tackle this topic. So if we could start with a quick question for you, Aurélie, from Akuo. Yeah, so the two projects that are being run, firstly the proof of concept and then the wider test case scenarios that are being run, I guess they look similar from the outside in that they're both island grid systems. However, they will perform different applications and perhaps may have other differences in design and technologies used. So I expect there's a lot of things at the moment you can't tell us about the tests, and that's completely understandable. But how might the tests be run differently for different types of projects? And how will this help to inform future projects from, you know, from design to testing to everything else?
Well, even though these two projects are both island grid systems, they do have very different applications. The Madinina plant is dedicated mostly to frequency regulation, whereas the Kuitawija project is used for energy shifting and renewable firming. And these are applications that are also quite frequent on continental grid systems. So I believe that from an applications point of view, we cover a fair part of the spectrum. However, the biggest difference I see here with some other projects is the chemistry. Well, these two projects do use the same chemistry, the same version of NMC. And indeed, if we consider future projects that may have, or other projects that may have different versions of NMC or use other chemistries such as LFP, we will indeed have to tackle these differences. And I think that for this, we would have to have other periods of testing, mostly, for instance, to calibrate the thresholds that are used for alerts, for instance, in order to adapt to these different chemistries or versions.
Okay, great. And I think, yeah, I think battery chemistry is something we might come back to a bit later on as well, and perhaps bring up the bring the PowerUp speakers into that one. But yeah, thank you very much for that, Aurélie. And you know, looking at the whole analytics suite, you know, a really vital part of that is data and having the right data, I guess. You know, in among the masses of data that are produced. So, you know, you mentioned, Arnaud, that data has to be clean to be useful. And what are some of the techniques or principles behind getting that clean data? And then how do you really determine which data is useful?
Yeah, thank you, Andy, for these questions, because effectively cleansing is an important step of the work we do. During this cleansing, all the data are analyzed to keep only physically meaningful information and remove all the outliers. To give few examples, we have sometimes false measurements from the BMS, false measurements of voltage, temperature, and so on. And so we need to remove these false values, because if we didn't do that, we will have some false alerts at the end. Sometimes we have also some issue of registration of the data from the SCADA itself due to interpolation and so on. So we have a specific know-how we have developed at PowerUp to do that. That combines both data science and electrochemistry to understand what we manipulate and to do the job very well.
Okay, so let's dive into a real world application of some of those principles you just mentioned. So if we could draw everyone's minds back to use case number 2. You referred to a cell imbalance being the main issue with the project, and you very nicely explained kind of how you were able to find those problems and essentially the economic implications of that. But can you just explain to us briefly, and I'm sure there's a degree of confidentiality perhaps involved if it's a customer system, but perhaps you could explain to us in general terms what went wrong with that asset. And I think our audience, some of them are going to be very highly technical people, some of them perhaps like myself, maybe slightly less so. So if you can explain to us what went wrong with that asset, and then after that, perhaps what some of the root causes of cell imbalances are and how analytics are able to detect those issues. But I'll know if you could maybe start off our answer on that, and if another speaker wants to jump in, then that would be great as well.
Okay, so thanks again for this question. If we talk about the use case 2 in particular, here the cell imbalance was due to a problem of state of charge dispersion. And in such situation, it can be managed by a cell balancing procedure. We can say that this type of problem is most often observed on LFP chemistry with a very flat behavior and problem of cell balancing more than for NMC chemistry. But so the point is that we are able to go into details and to determine, thanks to analytics, the root causes of cell imbalance issues. What the BMS is not able to do. For the BMS is going to track the difference in terms of voltage and is not able to tell you that this cell imbalance is due to the state of charge or to the resistance or to the state of health dispersion. And this is the point. Thanks to the knowledge, we are able to do the right maintenance, because if you have a state of charge dispersion, it's not at all the same, and it's not the same maintenance plan you need to do if you have resistance or state of health dispersion. So it's a key point, I think, and we bring knowledge, additional knowledge compared to the battery management system. I don't know if I answered to your question, Andy.
No, I think you did. I think you did very nicely, Arnaud. Sorry, Philippe, was there something you wanted to add on that one, or?
No, I think Arnaud was very complete, so I'm good.
Excellent. Okay, no problem at all. But kind of moving on a little bit from there, though. So you mentioned obviously the NMC is perhaps a little bit easier to monitor than lithium iron phosphate. We do really see, however, the industry largely moving, particularly for large scale stuff, more towards predominantly lithium iron phosphate or LFP chemistry. So Aurélie, I think you did refer to this briefly in your answer to the first question, but if you maybe just more generally explain how Akuo considers these differences in lithium-ion battery subchemistries when it comes to applying battery analytics on its projects, and maybe a bit more particularly with regard to LFP, I guess. And earlier on we talked more about different types of NMC, but I think as you broaden out that to more different types of lithium-ion battery.
Yes, I think that in the case of LFP, we would have to use the analytics that would be able to give a better estimation for SOC calibration, because this is, the SOC calibration is a way bigger subject for LFP than for NMC. And so here battery analytics could help us perhaps with the SOC calibration subjects on LFP, way more than for the NMC, for which the subject is maybe not as important.
Yeah, just adding to this just a little bit, if you don't mind, Andy. So it's important to mention that we at PowerUp are able to actually monitor all kinds of lithium-ion batteries, all types of chemistries within that family, right? So, and the two you mentioned are of course of greatest importance, and we see customers pointing out to us differences and concerns they have over performance and safety of those different battery chemistries. To take a few examples on performance, Aurélie just mentioned it. There are, rather complex approaches where analytics can play a role based on the combination of Coulombic method and Kalman filtering to accurately estimate LFP battery state of charge. And that it is really important not to see those deviations happening and to avoid unneeded calibration. Now, NMC cells are less prone to those deviations, but we should still see, in the case of cell balancing issues due to state of health or state of charge dispersion, those cells, those NMC cells can be overused at low state of charge levels while the battery is out of power, and that has an impact on performance. Then taking another example more on the safety parts of things. So generally speaking, NMC cells are less stable than LFP and more subject statistically to thermal runaway. That's true, but it's, we should still highlight the fact that LFP batteries are also prone to cell imbalance issues and associated safety risks. While safety incidents for NMC cells are more likely to stem from lithium plating phenomena. So what we can say from those examples is that battery analytics will help monitor those issues wherever they come from, and really help to find them quickly and find an efficient maintenance window to resolve them as fast as possible. So there can be different chemistries can lead to different issues, all of which can be identified via battery analytics.
Excellent, excellent. Thanks so much. And I think the NMC versus LFP debate is one we've heard so much about, and perhaps now is not the time to enter into a long conversation about that, but I know it's definitely something that most of the people watching do think about. So thank you so much for your regard of that to all of you. Yeah, so I mean, we're talking here about an industry that is in a real scale-up mode, I think it is fair to say. And Aurélie, you mentioned that there's 130, was it 130 megawatts or 130 megawatt hours? Forgive me, I couldn't remember which you said.
Megawatt hour.
For megawatt hours, right, sure, of battery storage in operation, but a pipeline of 3 gigawatts of development that Akuo has at the moment. So from those two relatively small projects, one of them the 3 megawatt, the other one 19 megawatts on those two island grids, from that to rolling out an analytics solution across a growing and increasingly large portfolio, what are some of the things that Akuo needs to think about really in that regard?
Well, for me, the key points here are standardization and scale up of the processes. The data that is generated in our plants and communicated to PowerUp needs to be standard so that we can smoothly replicate our data flows throughout projects. The processes of monitoring and alerting on our side should also be thought of globally, while of course still taking into account local differences. And this is something that we have kept in mind since the beginning of our work on the subjects in order to maximize our efficiency.
Excellent, excellent. I think that's something I find so interesting. I think we've had, there's a couple of projects we've seen to, increase the standardization and interoperability of digital technologies across energy storage, and I think that's really going to be something that's so fascinating to watch develop, I think, in the coming years. Okay, and looking back on those use cases or the case scenarios that you presented us from PowerUp, Yeah, so there was a mention of preparing analytics solutions for second life batteries. So these are batteries that are repurposed from electric vehicles generally. They're not always necessarily used electric vehicle batteries, but they were intended to be used for electric vehicle batteries, if not already used. So yeah, and they may be a niche, but I'm hearing that they will be quite a significant niche within the industry, particularly with supply chains being as they are. So yeah, so what are some of the key differences or challenges that exist with Second Life that you may not have with so-called quote unquote new batteries?
Yeah, I can take this one, Andy. So it's a really good question. I think, second life applications are still heavily debated in the industry, whether they will eventually be economically viable or not. But it's true that we will see a huge quantity of modules in the next years made available with still 70 to 80% state of health, for instance, indeed, as you just mentioned, from electric vehicles having reached their maintenance limits. So 70 or to 80% state of health is still a large number when you think about it. And we have been monitoring an ESS system in Asia, so a stationary storage system that was built from Second Life modules, actually buses, if I remember correctly, electric buses. And while doing this work, we saw quite a few issues due to the dispersion of quality and performance of those modules. And that was leading to a lot of safety alerts, some of which critical. So, I mean, all in all, I think it's perhaps even more important to monitor these second life assets than it is to monitor first life assets, although both, of course, have their own issues. But I think it's important also whenever monitoring a first life asset to care about the end of life of those systems, to know very well how those modules and racks are evolving in time, to give them a passport of second life, if you can say so that it's easier then to optimize their potential second life applications. And that's what we are planning to do.
Perhaps I can add one more information regarding this second life application. Because effectively, as already said by Philip, we have already analyzed some batteries in second life application, and we have seen effectively a higher level of dispersions, more often alerts and so on. So it's very important to monitor them in the second life. But I think analytics can play a key role also on the selection of batteries for second life. I explain my point. For the moment, we consider only the state of health values, and we consider from 70%, for example, from state of health, the possibility to go to a second life application. But in fact, two batteries at the same state of health levels can be very different inside. Some can have some lithium plating, some without, some can have a solid electrolyte interface, some without, and so on. So depending on the usage, you have different aging mechanisms. And so at the end, you have different batteries, even if the state of health values is similar. So it's one additional point that analytics can bring in the game to tell you not only the state of health, but also what is the aging mechanism. And so if you have some lithium plating, for example, you are not going to reuse this battery. You must go directly to the recycling process. But sometimes effectively you don't have any lithium plating at all. And it's a huge opportunity to reuse this battery. And we have validated with CA, for example, that with a very aged battery at 70% of state of health, we have validated that we can perform more than 4,000 cycles again, because we change, of course, the usage conditions. It has been validated in lab, so it's a reality. We can do some second life, but again, sometimes it's a very bad idea. You need to forget the second life story.
Right, okay. And Yeah, I mean, as I say, it's a niche, but some analysts are telling me don't underestimate that niche, of second life batteries, I guess. And it is a super interesting concept, I think, particularly because obviously electric vehicles slightly longer on the market than stationary batteries, perhaps. So you'll start to have some coming on stream, batteries that potentially customers will be using, I guess. Okay, so one last question from me, but a fairly big one, I hope, before we move on to the audience's questions. And we've heard this a few times before, and it's something that you very eloquently explained, but the cost benefits trade-offs, I guess, between operational to go earn revenues and management of the battery. Those cost benefit trade-offs are now part of the business case for battery storage, and is perhaps better understood now than a few years ago, certainly. Can you explain what some of the key metrics are in figuring out a good balance between costs and benefits, and what that means for customers, if it's not too abstract a question, I guess?
No, I think, Andy, it's a key question. I mean, I think you're spot on, and it's really putting us back into the economic benefits that we can bring to the market and to the industry. I mean, it was, I think, demonstrated probably by Modo quite a few times in recent events. I remember a slide indicating a very strong correlation between asset availability and asset profitability. So we're all into those cost benefit trade-offs, right? We need to make sure the asset is operating correctly to get the highest profitability. And I think all the metrics we discussed today on safety and performance enable, in the end, better decision making on those cost benefit trade-offs. For instance, deciding on the right timing for a maintenance window to restore detected imbalances and then gain asset capacity without putting safety at risk is one example. You want to make sure you're not, increasing your costs versus the benefit you can get off getting this asset capacity back. Another example is tuning usage parameters to optimize the remaining useful lifetime, like temperature. As an example, temperature control can have a huge impact on battery aging. So if you decide to go with a few degrees higher in your containers, that may translate into direct OPEX savings, but at the expense of smaller asset useful lifetime. And so you would eventually lose revenues due to that shorter lifetime. So, I mean, asset traders are more and more confronted to such critical trade-offs in their daily decision making. And I think they welcome the ability to get precise metrics to help them making the right economic decisions, and more importantly, taking all those critical parameters and KPIs into account that we can provide them on a daily basis.
Sure, absolutely. And if I could just do a very quick follow-up on that before we move on. I mean, I think, we see that the markets for battery storage that battery storage can participate in are kind of changing over time, sometimes quite quickly. So I was talking to a developer in Canada that was saying that they want to develop battery storage projects of over 100 megawatts. And they said they don't necessarily know what applications those batteries will be doing, from let's say year 5 to year 7 as the market changes, in particular. They're opening up ancillary service markets, plus, changes in power trading and stuff. So I don't know if there is anything to be said about that at this point, Philippe, but yeah, I mean, could you maybe tell us about PowerUp's approach to how it might consider that, battery storage systems, changing applications and performance that it will be doing over time?
That's a great question again, and a great extension of the previous question, but it's true that we've seen from several customers and prospects an interest to expand their services versus the initial thoughts. And that can be due, for instance, to declining revenues on ancillary services like frequency regulation as an example. And so due to these declining revenues, there is an intent to augment the potential service mix towards additional services coming in during the lifetime of the asset. And that has an impact, obviously, on the agreement that's been done initially in terms of the asset lifetime. It can, have an impact on also on the way the asset will be suddenly cycling with a much higher number of cycles per day. And so they welcome our ability to simulate the impacts of those changes on their assets. And that's, I think we need to be very flexible. We need to give them that flexibility and that visibility onto how their assets going to be evolving in time due to changing service mixes, as an example.
Excellent, excellent. All right, well, thank you very much for answering that question as we went along. Okay, so lots of audience questions here, and we've got just under 10 minutes to take them on. One of the audience members suggested that we might not be able to answer all of the questions live. You are correct. We will not be able to answer all of them live, unfortunately. But there's a high volume of good questions. And as I said before, PowerUp and presumably Akuo as well will be delighted to continue conversations offline. So we'll start with perhaps a quick, and I don't know if an easy one, but Nuria from the audience was asking, what indicators do you use to assess the state of safety? And if we could, you know what, let's see if we can tackle two of these at a time. And then Peter also asked, how often do you read battery data, and to what level? Is that to rack, to module, to battery cell level, etc.? So if you could perhaps start off with a quick discussion of state of safety, and then explain how often you read battery data and to what level, that would be fantastic.
Okay, so I can try to answer these questions. Regarding the first part of the questions, if we consider the state of safety definitions, we are going to track several things. First one is over voltage and under voltage. We're going to track over temperature, but I have to say that it's quite late detection compared to the thermal runaway phenomenon. And the most important part is the cell imbalance that we're going to track, because hence it's a very, very early detection compared to the thermal runaway, since we are going to be able to track a new time the resistance dispersion or state ovals or the state of charge. It can lead to the growth of lithium metal dendrites, for example, leading to internal short circuits. So it's very, very important to track such a phenomenon. And it's very complementary to BMS again, because the BMS is blind. If we think about the state of charge dispersion when you have a LFP chemistry, you can have a huge state of charge dispersion without any voltage difference, and so your BMS is blind regarding this aspect. So this is a definition of what we call a state of safety, to have early signs of all the events that can lead to the thermal runaway, and so including the growth of metal dendrites, that can be the copper on the positive side, that can be the lithium on the negative side. And regarding the second part of the question, so at which sampling we need to collect the data, of course, sometimes it depends on the C rate of charge and discharge, that means the intensity of current, but most of the time, 1 minute down to 10 minutes is enough to have very accurate indicators, including state of safety. So global view is we can deal with 10 minutes sampling. 1 minute is better. That's the answer.
Okay, fantastic. And yeah, more questions on thing. Yeah, sorry.
The last point was regarding the level, rack or module.
Oh, sorry.
Yeah.
It was.
Yeah. Perhaps I can add just one point. We can address both. Most of the time, we have just the data from the rack level. And so we can do all the indicators at this rack level. A few times we have module level, and so we can address both. And so you have a better view, of course, because then you can directly go to the faulty module when you detect it. But when we have only the rack level, it is also possible to point directly to the faulty module, because most of the time we have the ID of the cells, as you know, of the voltage and maximum voltage, minimum voltage, and so on. We have an additional measurement of the ID, and thanks to the ID, you can directly point to the faulty module. Not sure that
excellent.
was clear.
Yeah, no, that was great. No, thank you very much. Thank you very much. Sorry to interrupt you there. So there's a question from the audience from Jesse. So Jesse, thank you for your question. Jesse asks, so specific to lithium iron phosphate, so LFP batteries, what state of charge accuracy can be achieved for LFP batteries, and are there certain calibration conditions that need to be passed?
So I can explain briefly what we do on the state of charge part. We are going to track the historical data, and first we analyze our own accuracy of our own gauge. And we consider that when we have plus or minus 2.5%, it is good results. And then we are going to compare these results with the BMS state of charge. And so we can say that we obtain this accuracy, whatever the chemistry, with NMC, with LFP, and without any procedure, because of course analytics is done online. So we don't have a procedure to fully charge, fully discharge. We have some other way to calibrate our gauge, even in the middle of the range of state of charge. This is the point. So we can say that the accuracy of our gauge is plus or minus 2.5, and it covers the different chemistries.
Okay, fantastic. We'll keep rattling through these, and I think we'll try and do at least 2 or 3 more questions, I think, before we sign off today. So a question from audience member Masashi, who asks, do you need any extra sensors to monitor BESS assets and EV batteries? I'm not sure that's really what we're focusing on today, but let's run with the question. So do you need any extra sensors to monitor the BESS asset and the EV battery? And is the data obtained from the battery management system, which is equipped by OEMs, reliable? Now, I've met some people who might find that last part a little bit controversial, but I'm going to leave what I've heard to one side, and I'll ask you guys what you think.
So effectively, whatever the applications, we collect similar parameters, voltage, current, temperature, and we don't need any additional sensors. For electric vehicles or backup systems, it's very similar to what we collect on battery energy storage system. But BMS accuracy on all these measurements is largely enough to our calculation. But of course, as already mentioned before, we need to have the cleansing step, very important, to remove all the false measurements from the BMS. But that's all. We have similar solutions for the various applications.
Right. So, I mean, and correct me if I'm completely wrong here, but I think the BMS is kind of good for kind of measuring on a minute by minute, you know, how and regulating how it's working. But what you guys do with analytics is kind of try and apply that and extrapolate it more over kind of the lifetime of an asset and where it's going. Is that roughly how you describe it?
We need.
Yeah, I think Andy, what you're trying to say, sorry, Arnaud, is that the BMS is good at doing raw measurements, right? Of voltage, current, temperature, is less accurate when trying to design state of health or state of charge. So that's where we are supplementing it or complementing it with additional accuracy. But the initial measurement capability, the raw measurement, is what we need as an input to our systems. And the BMS is very good for that. It's just that we believe that the analytics are, adding an additional layer of accuracy, precision, computing capabilities, etc., that the BMS will not have. Looking at the asset as a whole, and being able to pinpoint specific issues that the BMS today cannot pinpoint. So yeah, we need the BMS to get our inputs. That's the important information here.
Absolutely. So yeah, I mean, it's a pretty important component, I guess, regardless of what the analytics layers are over that. But so question from Faisal in the audience, and thanks for your question, Faisal. So Faisal asks, in your cloud solution, do you provide features for optimizing operations of an asset? So the example Faisal gives, if I were to benchmark against how a battery is operated versus how it could have been better operated, so I guess the opportunity cost of running certain applications versus other applications, doing maintenance at certain times versus other times, or different routines for the battery. Yeah, just wondering if you've got a view on that question, really. I guess how you kind of benchmark performance. And I don't know if this is perhaps something that Aurélie you'll be considering from an Akuo perspective as the tests roll on. But yeah, who'd like to answer Faisal's question?
I could start simply by saying, yeah, we are already analyzing the usage parameters, and directly those usage parameters have an impact on all kinds of operating parameters. In terms of lifetime, we discussed the correlation between temperature and lifetime as an example, but it also can lead to accelerated aging. So we are able to benchmark the different constituents of an asset down to the module level, and we will see that some modules will have a lower SOH, state of health, than others, and that may be the sign that they have issues that need to be looked into. And so we're able to recommend actions, maintenance actions, to replace, the least functioning modules, as an example, or adjusting cycling and temperature to stay within the recommended ranges. And all of those actions have an impact on operations. So in a way, we are doing this benchmark continuously, and we are providing recommendations on how to improve and optimize the assets on a continuous manner. So that's really what we are bringing to the table.
Okay. You know what? I think we've run just over time, but we're going to do, if everyone's okay with it, we're going to do 2 more quick questions. I think, we want to give the audience as much value as possible, even though it's a free session. So Mulugeta from the audience, thank you for your question, Mulugeta, is asking, how do you assess state of health when battery storage systems are providing multiple services that need to meet several technical requirements? So increasingly we're seeing batteries doing, so-called stacked applications. What sort of bearing does that have on the, the analytics in terms of state of health, or, perhaps in terms of other things that you might be looking at?
Yeah, to answer to these questions, perhaps we need to distinguish the state of health from the remaining useful lifetime. Sometimes it's not so clear. What we do both, but first, for the state of health, it's an opportunistic approach. I mean, we use partial charge, partial discharge. We need a state of charge range around 30%. That means 30% of depth of discharge is enough to have a very accurate state of health at 2% plus minus 2%. And so when you have different services, you have different usage, but it has no impact on the state of health evaluation. If we consider the remaining useful lifetime, if you have different services, then we are just going to take into consideration this usage profile and to simulate, thanks to an aging and dynamic aging model, to simulate this usage. So you can select every usage you have. And you can have, of course, different services, and it can change, as already mentioned before. Your service can change over the time, and we are going to take into consideration this new usage for the remaining useful lifetime estimation.
Okay, so multiple stacked applications, not necessarily a barrier to being able to make those important kind of assessments.
Exactly, yeah.
Okay, cool. Okay, last question, and it's maybe a big question that you'll want to consider and discuss offline with the questioner, but Kartikeya from the audience, thank you for your question. Kartikeya asks, is there a baseline performance measurement criteria for battery energy storage systems? When companies claim to have improved performance or improved kind of degradation profile, what's the widely accepted comparison methodology, if there is one? And as I say, perhaps this is a bit too complicated to go into in full right now. But I don't know if there's any sort of key points or key takeaways that you think our audience should consider when it comes to making comparisons and listening to the claims that manufacturers and perhaps the operators of battery storage systems make.
So I believe one KPI that even Oli was showing up on her slides was availability, and I think we've been required to build that KPI as more of a synthesis of how well the asset is functioning and how we can improve its availability throughout operations. And as I already mentioned, this is very strongly correlated to the overall profitability out of the asset. So I believe one answer could be availability, but then there are multiple definitions there, but maybe converging towards one unique definition could be interesting, and then benchmarking assets over that definition is definitely one possible answer to that question. But maybe Oli, you want to expand on that?
Yes, I agree with you, Philip. I think the main KPI is availability, and indeed it takes into account many different components. It's not there are several ways to define availability, but I think this is the most accurate KPI we could use, at least for performance.
Excellent. Okay, well, as I say, we have run a little bit over time, so thank you so much to everyone that stayed with us. As I say, you can watch this session back on demand at your leisure, and it will be on our YouTube channel as well in a few days' time. As mentioned, you can meet the team from PowerUp at Intersolar next week. I'm not going, unfortunately, but I wish I was. I've been about 6 times, and it's always a fantastic show to be at. But if not, we will be still here at Energy Storage News, hopefully working hard to deliver you insights and comments on the industry. So I just want to thank all of you that are involved in this amazing, tremendous, dynamic industry, first of all, and please keep up the hard work. It's awesome technology, and well, we all know what's at stake, really, I guess. But further to that as well, I would love to thank our fantastic speakers today. Aurélie, thank you so much for joining us. And to you, Philippe and Arnaud, as well. And with that, I guess that's really pretty much all from us, but to say thank you for joining us, and goodbye for now.
Yeah,
thank you very much.
Thank you.
Thank you. Goodbye.
Bye-bye.
Goodbye.